Hi, thanks for joining me today. I'm going to be going over problem 3 from the Imperial College Maths competition from the second round in 2021. Okay, I'll leave a link in the description below where you can find more details about the competition. Anyway, this is the problem we're going to be tackling today. We have f, g and h being real-to-real continuous functions, and we have a random variable x such that the expected value of g of x times h of x is 0, and the expected value of g of x all squared and the expected value of h of x all squared is strictly greater than 0. We want to prove this inequality here holds, this sort of big, ugly looking inequality here. So on the left hand side we have the expected value of f of x all squared, and we want to show that that's greater than or equal to this guy here. So the sum of two fractions, the first fraction is the expected value of f of x times g of x, then we're taking that expectation and squaring it, and then on the bottom we've got the expected value of g of x all squared. Okay, and then the second guy here is the exact same thing as this thing here, except with the g's replaced with h's. So here we've got the expected value of f of x times h of x all squared, and then on the then the expectation of that all squared, and then on the denominator we've got the expected value of h of x squared. Okay, so we want to prove that this inequality holds. If you want to have a go at this problem, pause the video now and give it a go for yourself, and I'm going to jump straight into the solution. Okay, so the first thing I'm going to do is introduce this new set V, and it's going to be the set of functions from the reals to the reals which are continuous. So the set of alphas from the reals to the reals which are continuous, such that the expected value of alpha of x all squared is finite. So in other words, the expectation of the square of alpha of x is finite. Okay, and what we're going to do is define this guy here, and it looks like an inner product, and we'll show you in a second that it is an inner product. But for any alpha and beta in V, we're going to say open bracket alpha comma beta close bracket is defined to be equal to the expected value of alpha x times beta of x. Okay, and we want to show that this guy here is an inner product. If you don't know what an inner product is, I've made a mini series to do with Gaussian quadrature, and in that first video I talked about inner products, so I'll leave a link for that video in the description below. So go and clue yourself up on inner products if you're not too sure. But all we're going to do is show that this is an inner product first. So that means firstly we'll check positive definiteness. So let's firstly see that it's non-negative. Alpha comma alpha is equal to the expected value. Just by looking at this, it's just going to be alpha of x all squared. But this guy here, we know because alpha is a real function, the guy on the inside is going to be non-negative, so certainly its expectation is going to be non-negative. Now we've got to check that it equals 0 if and only if alpha equals 0, but that's not too difficult to see. Alpha comma alpha equals 0. Well, that's if and only if this expectation equals 0, but then that means that alpha x all squared equals 0 almost everywhere. But because alpha is a continuous function, we can get rid of this almost everywhere, and we get this guy here, and of course just square rooting both sides gives us this guy here. Okay, so this is a positive definite thing. Now symmetry is quite obvious. If I swap the beta and alpha, I swap the beta and alpha here, because of sort of commutativity and multiplication, of course it's the same thing, and linearity is also clear, and that comes directly from linearity of expectation. Okay, so this guy here is indeed an inner product. Now what we're going to do is clear up the whiteboard and use the fact that it's an inner product, and hopefully that's going to tempt out some Cauchy-Schwarz to get the desired inequality. Okay, so now what we're going to do is introduce y. It's going to be f minus lambda g minus mu h. Here, lambda and mu are just some arbitrary constants which we're free to choose, and we'll choose them in just a second. Now what we know is from the definition of an inner product, y inner product itself is just is non-negative. So this guy here is certainly greater than or equal to 0. Okay, but we can just plug what we have our definition for y is into here. So this is f minus lambda g minus mu h, f minus lambda g minus mu h, like so. Then use the linearity of the inner product to get that this thing here is equal to f with itself. Then we're going to get minus 2 lambda fg. So that's from this f and that minus lambda g, and then the minus lambda g f, and then just using symmetry of the inner product. Similarly, we're going to get minus 2 mu f with h, like so. And then we're going to get from the g's, the lambda, minus lambda g times minus lambda g gives us a plus lambda squared g with itself. Then we're going to get a plus mu squared times h with itself. And then the only things we've got to consider now are the g's and then the h's. So the g from this side and the h from this side, and the h from this side and the g from that side. But if you remember from the sort of assumptions in the question in the preamble, we assume that the expected value of g of x times h of x is 0. So those inner products will just evaluate out to 0. Okay, so we have 0 is less than or equal to this guy here. And remember, lambda and mu, we're free to choose. Okay, so what I'm going to do is simply choose mu, or lambda, sorry, because obviously we're free to choose lambda and mu, and we want to get to our inequality. So we're going to choose lambda to be equal to fg divided by gg. Okay, and we're going to choose mu to be equal to fh divided by hh. Okay, like so. Now, I'm not going to go through all the details. I'll leave it to you to plug these into this inequality here, and sort of there'll be some nice cancellations and stuff, and then rearranging will get the desired inequality, bringing this, or keeping this ff on this side is greater than or equal to, bringing everything onto the other side, and then we'll get the desired inequality. Of course, recalling the fact that this inner product is just the expected value of, alpha inner product beta is just the expected value of alpha x times beta x. So recalling that will give us the desired inequality, but that's just kind of boring and rearranging, so I'll leave that to you to do. But yeah, this is a nice sort of short solution to this problem. I hope you have enjoyed it, and I guess one thing we can note from this solution is we didn't really use too much knowledge about probability or expectations or anything like that. Most of this stuff holds in the general sense, so we didn't really need to worry about expectations. This mainly was an inner products question in disguise. Anyway, I hope you have enjoyed this video. Do check out the solution videos I made to the other problems as well. I'll probably make a playlist or something on this channel. And also, if you want to see the problems from round 1 and their solutions, I also made solution videos to those as well. Links to the playlists will be in the description below. Anyway, thanks for watching. I'll catch you in the next one. Have a great day.